A very warm good morning to one and all. So this is Advanced Thermodynamics and Combustion course, as we all know, being conducted under NPTEL program by IIT Guwahati. And this will be the last session in the series of these live tutorial sessions. And this session, rather than being a problem solving session, it's a course concluding session. Okay, so here we will be briefly discussing all the topics that have been covered uh, in the span of this course, right? And instructor for the course has been Professor Niranjan Sahu from Department of Mechanical Engineering, IIT Guwahati, and my name is Aditya Sharma. I am a teaching assistant for these live tutorial sessions, also a Prime Minister's research. So we shall start in a couple of minutes. Till then, let's wait and then we shall start the session. Thank you. Okay, so I believe we can start with the session. So I was telling that this will be the course concluding session. Here we won't be solving problems, but we will briefly uh, revise the topics, all the topics that have been covered in the span of this course. Okay, so it will be kind of revision. All right. So if you wish to continue with this session, so it's up to you. So we won't be solving questions in this, and the video will be available later on YouTube, as is the case with the other tutorial sessions. Okay. So we have 2 hours. So let's see what we can touch upon. Right. All right. So the course is Advanced Thermodynamics and Combustion. So there are sections in this course, right? So in first section we deal with core thermodynamics, right? And then later on we have discussion on mixtures, right? And then the last section is on combustion. So these are broadly the three sections that are there in this particular. The first is your on thermodynamics, fundamentals of thermodynamics, right? Concepts of thermodynamics. And then second section is your gas mixture. So this is from the perspective when you're in combustion, your fuel and oxidizers mix, right? They give rise to a mixture. So in that scenario, when we have to do the thermodynamic analysis, so from that perspective, discussion has been done. Later on, we come to combustion, right? Where we see different aspects of combustion. So we will see, try to revise these one by one. So in your week one is basically your review of basic thermodynamics, right? Here we see laws of thermodynamics. So first we saw your zeroth law of thermodynamics and how do we define a thermodynamic equilibrium based on your zeroth law of thermodynamics, right? Then we defined also what is a hydrostatic system. So hydrostatic system basically is an isotropic system, right? Which has properties in all the directions same. And when we are defining a hydrostatic system, we assume that there is no gravity, electricity, or magnetism, right? So here we, so I'll just jot down some formula also that are there in these discussions, right? So first is your volume expansivity. Okay, so that is written by, this is 1 by V at constant pressure, right? So in this hydrostatic system, we also saw what is uh, isothermal bulk modules. This is right, and then isothermal compressibility is just reciprocal of it. Right by this. Then we move on to our first law of thermodynamics, which is basically the law of conservation of energy also, right? So from here we have this expression. I'll just jot this down. So all the topics it is not possible to discuss, but at least we'll get the gist. Okay. So where U is for internal energy and other nomenclature is standard, right? So this is your first law of thermodynamics. After that, we saw second law of thermodynamics where uh, Calvin Planck's statement was discussed, and then Clausius statement was discussed. So your Calvin Planck's statement is with respect to your heat engines, and your Clausius statement is with respect to your refrigerator. So Calvin Planck's statement basically says that through an heat engine, if you wish to get a work, so some amount of heat has to be rejected. It is not possible for a heat engine to convert all the heat that it is receiving to, right? Right. Then is your Clausius statement for refrigerators, which is that if you want to move heat from a low temperature to high temperature, in that case, some outside work is always required to do that. Without this outside work, you won't be able to do the refrigeration, right? So this is your process statement. So these were the basic concepts that are discussed in your week one, right? Okay. Then your so as I have told that first section is your concepts of thermodynamics, right? So in this series, your second week is on entropy and exergy. So two new concepts have been introduced, right? First is your entropy and then is your exergy. So what is the need of introducing these concepts? So all this is under this topic, right? Okay. So one by one, we let's see the topics. Okay. So first is your Clausius theorem and second law. So what does this theorem say? It says that if we have some cyclic process, so this is your weak two, right? Entropy and exergy. So it says that entropy and exergy. So your Clausius, what does it say? It says that your cyclic integral of this will be zero if process is reversible. Okay. So this is your Clausius theorem, right? Also, now from here we define entropy also. So if your system is your thermodynamic system is moving to some state F from initial state I, right? In that case, its entropy is defined this way. Now, what's the catch here? Catch is though your heat transfer, right? It's a path function. But if you see the entropy, it is path independent. Okay. Yes. I was saying that other than this point that your entropy is path independent, it is also that your entropy is an exact differential, right? So we just got an integral of your dq above upon t, and this way we could change your this q that is path dependent to a property which is path independent, right? So with the help of this, what we can now do, we can take help of this property to analyze our thermodynamic system in mathematical way, right? So when we have to deal with differentials in that scenario, this property turns out to be very handy. Right? Okay. So this was your entropy, right? Then is your entropy evaluation, right? So now to evaluate this entropy in different scenarios, how do we do that? For your entropy change, these formula can be used. Okay. Or all right. So your entropy can be evaluated using these formula, right? So there are other formula also, but these can also be used. Right? Then is your temperature entropy diagram. So in your temperature entropy diagram, the slopes. So if you see your slope of temperature entropy diagram, so at constant pressure, this is this, okay, and at constant volume, this is this. All right. One more topic that is there in this week two's content is inequality. So from Clausius theorem, we see that for a reversible cyclic process, dq by dt is integral of dq by dt is zero. But for irreversible processes, what is this? This is less than zero. Okay. So this is your Clausius inequality. And then from your irreversible processes, heat and entropy. From this topic, one important inequality that comes out is this, which is this. Okay. So your change in entropy will always be greater than equal to this ratio. Correct? After this comes a very important topic as far as the thermodynamics is concerned, right? This section of the concepts of thermodynamics is concerned, right? So which is your entropy balance? So entropy balance has been done in two scenarios. For two scenarios, one is your closed system and one is your case when we deal with the control volume. So closed system is closed system, right? And then in control volume case, what is there? We have some flow, and out of that flow, we take some particular control volume of our interest, right? And we try to balance the entropy in that particular space only, correct? So expressions for this I'll write. So this is this. Now one important term in this expression is your sigma, right? What is this sigma? What does it signify? So it signify entropy production. Now, what do you mean by entropy production and when it is significant? So, entropy production basically is significant in the processes which are irreversible, right? In non-irreversible processes, you won't see entropy production. But then the processes which are irreversible, there you see this sigma type, right? So this is important for your entropy balance. And the other term is for your heat exchange across your boundaries. Okay, boundary of the system. So this way we balance the entropy for our closed system. Then is your entropy balance for your control volume. So for a control volume, the expression is this way. So here we define this balance by taking the entropy with respect to time. Okay, the change in entropy in the control volume with respect to time. Okay, so this is this way. So this term is for your like in the previous case. This is for your heat exchange across your boundaries. Okay, so we will write this first. So this is your entropy production rate in your control volume. Then one additional thing here is, see why this term has been included in the entropy balance of control volume is because entropy is an extensive property, right? So when there is some mass entering in the control volume and some mass exiting the control volume. So when some mass is entering, it is bringing some entropy with it, right? And when some mass is exiting the control volume, it is taking out some entropy from the control volume, which is the system of our concern, right? So this is the significance of these two terms, which have been added in when we see compare with the closed system entropy values. Okay, so this was about your week two. So your week one was basic thermodynamics, and week two was discussion on only entropy. So week two and week three are combined themes. Okay, right. So in your week three, you basically have discussion on your exergy. Now, what is exergy? So exergy basically is the maximum theoretical work that you can get from system in simple terms. So exergy fundamentally is work. Okay. But then what work? So it's theoretically the maximum work that you can obtain from a system that is exergy. Okay. All right. So before the start of your exergy topic, some isentropic efficiencies have been mentioned in the week three topics. So I'll just write down the isentropic efficiencies in different devices. So for your turbines, this is so your denominator is your ideal case, and then your numerator is your actual case. Okay. Ideal case where your entropy remains constant. Okay. Then is your efficiency of the nozzle. So it is in term of velocity at the exit. What will be in the isentropic case and what is in the actual case. Then third is your compressors or pumps. Here your efficiency is this one, right? So this is your isentropic efficiencies for different thermal devices. Then comes the concept of exergy. So as I've already mentioned, this is the maximum theoretical value of work. And one important concept here is of a dead state. So what is a dead state? So initially your system will be in some thermodynamic state, right? And your environment, the environment of the system will be in some other thermodynamic state. So as some thermodynamic process takes place in your system, it loses its exergy, right? And then if it is losing its exergy, it will tend to move towards the dead state or the state that is of its environment, right? And reaching this dead state, there is no further possibility to obtain some work from this system, particular system. Okay. So this is your dead state. And how do we define, how do we denote a dead state? So we in the subscript we use not, okay, zero to denote the dead state. Okay. Then when we mathematically define exergy of a system, so how do we do this? So exergy is written by E, and this is difference in your internal energy. Then this, then so this is your T naught V minus V naught, then T naught S minus S naught. Okay, here S is your entropy. Then is your kinetic energy terms and your potential energies terms. So these are also the changes, right, with respect to your dead state. So knots here all correspond to your dead state. This is your expression for dead state. Now the same way as we did the entropy balance for closed system and controlled volume, here also we have done the balancing of the exergy of a system for both the closed system and the control volume. So what is the exergy balance for your closed system? this is so if the system is moving from state 1 to state 2, in that case, if we have to balance its exergies, so how do we do that? Okay, so this is your exergy balance for a closed system. Here, this is for your exergy destruction because of irreversibilities. Okay, so when your system is moving from your state 1 to state 2, some of its potential to perform some work is destroyed, and the cause for this is irreversibilities. And how do we mathematically include it in the balance? So this is your T naught into your sigma, where sigma is your entropy production. So, so this is your exergy destruction, and this is your transfer of exergy. Okay. If you see this, this is your transfer of exergy. All right. Then is your exergy rate balance for control volume. Okay. So this is change in exergy with respect to time minus this. Now, as the entropy was an extensive property, same is the case here. Exergy is also an extensive property, so it depends on the extent, okay, of the substance. So this is your exergy rate balance for your control volume. So it has, like in the above case, there is transfer of exergy in these terms, okay, and this is your exergy destruction term. Then also the last topic that I'm going to discuss here is your second law efficiency, right? I'll just write the expression for this. So your second law efficiency is also known as your exergetic efficiency. Okay. So this is now U here is for the end use. Okay. U is for your end use and S is for your source. So if you see T subscript U is the end use temperature and T subscript S is the source temperature. So this way the exergetic efficiency of a system can be calculated using this formula. So these were the first 3 weeks. Then your fourth and fifth week is on your thermodynamic property relations. So these are the relations between different properties, thermodynamic properties of a system. Okay, and these relations prove to be very useful in our thermodynamic analysis. So in this week, first we saw how we get our Maxwell relations that are basically the property relations, and then using these property relations, how can we calculate the properties when some phase change is taking place, right? So for that we saw equation, this Clapeyron equation and Clausius-Clapeyron equation, right? Okay. So Maxwell relations, though I won't be deriving Maxwell relation, but how can we do that? That I can tell. So, so let's say we have some function that is z, which is a function of z x and y, and this is an exact differential. So if it is an exact differential, in that case we can write it in this form. Okay. Now if we give this term m denotation and if we give this term n denotation, in that case this becomes dz equals to m dx plus n dy. Okay. This it becomes. Then for exact differential, they have some property, and that is this. So using this property of exact differentials, we can derive these Maxwell relations. Okay. So there are four Maxwell relations, and then eight basic relations, and then further four additional relations that can be obtained from these eight basic relations. That is basically a comparison. Based on that, we can get these relations. Right? So for Maxwell relations, please keep in mind this exact differentials concept, okay, and the property of these exact differentials. Right. Then for your phase change processes, we have two equations. One is your Clapeyron equation, and then is a Clausius-Clapeyron equation. The Clapeyron equation can be written this way: d by dt of P in saturated state is equals to, so this shows enthalpy in gaseous state and enthalpy in this liquid state, that is F, denoted by F. So this is your Clausius-Clapeyron equation. So sorry, Clapeyron equation. Then your Clausius-Clapeyron equation is just an extension of Clapeyron equation, which is so this is your Clausius-Clapeyron equation. So these two equations have been given for your phase change processes that have been discussed in your week 4, along with your Maxwell relations, the derivation of Maxwell relations. Okay. Then your week 5 again is on your thermodynamic property relations. Here the important topic is your first throttling process, then what is your Joule-Thomson coefficient. After that is also the liquefaction of gases, which is based on your throttling process. Okay. So what is your throttling process? So throttling process basically is that we are passing our fluid from some narrow passage, right? And this leads to its decrease in pressure. So that is throttling. But in scenarios with your throttling process comes the decrease in temperature also. Okay. So this decrease in temperature can be used to liquefy the gases, right? By means of throttling process, the liquefaction of gases can be done. And the graph of it is this way. I'll draw so this is your week 5. So the throttling process, right? Graph is like this. So your throttling process basically is an isenthalpic process. Okay, where the enthalpy remains same, right? Okay. So this is your combustion. So first of all, it's an isenthalpic state. Other than this, the point is that as we are throttling some fluid, first of all, in the first phase, its temperature will increase, right? But then a state will reach from where your temperature starts decreasing, right? So that state is your inversion state. Okay. So this and also this decrease in temperature, as I was discussing, that it can be used to liquefy the gases. So this second section can be used to liquefy the gases. So this is your graph for throttling process. Okay. And then there is one coefficient, that is the slope of this graph. So this is your Joule Thomson coefficient, which is uj, and this is change in temperature with pressure at constant enthalpy. And this can be calculated with one of your thermodynamic property relations that you have derived, okay, in the previous week. That is week number 4. All right, so this is your week number 5. So week 4 and week 5 are on thermodynamic property relations. Then is your week number 6. So your week number 6 is on properties of gas mixture. So firstly, so this first section of this course is over. Okay. From week 1 to week 5 is the first section in which you discuss the concepts, different concepts of thermodynamics, where we saw concepts like entropy, entropy balance, exergy balance for closed system for a controlled volume, Then also we derive the thermodynamic property relations that can be used to analyze our system. Okay, different in terms of its different properties, be it temperature, be it enthalpy, be it entropy, be it Gibbs function, be it Helmholtz function. So all this can be done using these thermodynamic property relations. So now is your mixtures. Okay. So for your gas mixtures, there are two weeks have been given. So week 6 and week 7 has been given. Okay. So we will start this, but before that we will take one short break of around 5 minutes, and after that we will continue with the session. Thank you. Okay, so I believe we can continue with the session. So we were on gas mixture. So this is the second section of our course. Okay. So here we in week 6 we learned real gas models. Okay. Then we saw relations of gas mixture, basic relations of gas mixture. Then partial molar properties of your gas mixture we saw. Okay. After that, two properties have been discussed. One is your chemical potential, and then is your fugacity. Right. So let's do these. So first is your real gas models. So this is your week 6. Properties of gas mixture, where we saw real gas models, out of which one is your van der Waals equation, which is this, where is molar specific volume, that is V by N. Okay, so this is your van der Waals equation. Then also we have another model, real gas model, which is your Redlich-Kwong equation. So this is so these two models have been discussed in the real gas models. After that, we saw the basic relations for gas mixture. So if we have different components in a particular mixture, so using the properties of those components, how we can get the property of the mixture as a whole. So for this, there are rules, different rules. One such is your case rule. So what happens in case rule? One example I can give is that, for example, if you want to find the critical temperature of the whole mixture, of the mixture as a whole. So if using case rule we have to find, we can do it this way. Where Y is the mole fraction of the yi is the mole fraction of the I component, right? This is your case rule. Then your another rule is your additive rule, where things are pretty straightforward. So one example is, so if you have to find the pressure of the whole mixture, simply the pressures of different components that can be added and we can get the pressure of the whole mixture, right? So this is your additive rule. Then next is your partial molar properties. So what are your partial molar properties? So this basically, let's say we have some property X, okay? So in a mixture, there are different components. Okay, one component is the ith component, and its property, partial molar property, can be written this way. So this is partial differentiation with respect to your moles. Okay, at some temperature, pressure, and your mole, number of moles. So this partial, the defining of partial molar properties can be used to define different properties. And one such property is your chemical potential. So now your chemical potential can be defined, and it is denoted by this. So this is basically partial molar Gibbs function. Okay, where Gibbs function is being partially differentiated with respect to your mole, number of moles of a particular component of the mixture. So this is your chemical potential. Okay. Then after that, we have fugacity. So what is the need to define fugacity? So the way in which fugacity has been defined, it plays the same role as is of the pressure, but there is one difference is there. That is, it improves the functionality of your mathematical function. Okay, mathematical expression. In what conditions? In the limiting conditions, right? So for example, if your pressure is zero, right? In that case, what the scenario will be when we are using fugacity. So let's see that, right? So first of all, I'll write one expression of chemical potential using fugacity, right? So this is one expression of, sorry, this, okay. Here F is the fugacity and this is the chemical potential. So this is the relation between chemical potential and fugacity. But then if you see the limit when pressure tends to 0 and F by P, this is 1, right? So P tends to 0 is the limiting condition, and in that limiting condition, the limit that we obtain of F by P is 1, right? So this way it is improving the mathematical functionality, right, of an expression in which it is there present. Okay, so this is your fugacity. After that, week number 7, that is properties of gas mixture. So in previous week we saw the real gas models and some properties. Now here the theme though remains same in this week. One important topic that has been covered in this week is your mixture composition. Though these are very basic things, but so the composition of mixture. So to define that, we first have mole fraction. These are basic terms, but then we must know. So Ni is the number of moles of some component in the mixture, and N is the total number of moles in the mixture as a whole, right? And then this summation is always equal to 1. So the mole fraction of all the components of a mixture, when added, they give you unity. And if we want to find the molecular weight of a mixture, how can we do that? It can be done this way, right? So, or you can write it MWI, molecular weight of some particular component of the mixture. So this way we can find out the, and then molecular weight of air. That is very useful when we study the combustion section. Okay. So this is your properties of gas mixture, right? Then we come to section 3. Okay. First, section 1. Then this is section 2. Then we are at section 3 of this course. Now section 3 is on combustion. Okay. Okay. This is your section 3. Right. So your section 3 starts with your combustion and thermochemistry. This is week 8. So here we see stoichiometry and heating. We will discuss stoichiometry and heating value of fuels. Okay. So what is a high heating value and what is a low heating value? And let's see this. Okay. So in your Stoichiometry. So stoichiometry is a very important topic as far as the combustion is concerned. So now air to fuel ratio, how do we define it? This is basically mass of air to mass of fuel, which can also be written as mass molecule. This m is the molecular weight of air, okay, and n is the mole number of moles. So this, and then equivalence ratio. So equivalence ratio is defined for your real case with respect to your stoichiometric case, okay, which is the ideal combustion. Stoichiometric combustion is the ideal combustion. So this is denoted by phi, and this is air to fuel ratio in stoichiometric conditions divided by air to fuel ratio in actual. Okay, so this is your equivalence ratio. So after that, heating values. So there are two types of heating values. One is your high heating value, and then second is your low heating value. So what are these two? So in your combustion products, you see that you have water as one of the products, right? So in some case, your water will be in liquid state, and in some scenarios, your water will be in evaporated state. So if your water is in evaporated state, some energy has been used. The energy dissipated in the combustion process has been used to vaporize the water. Okay. So in that case, the energy of use to us will be of some quantity that is less if we compare to the case where your water is in liquid state. Okay, because there the energy is not being used to vaporize the liquid, right? And in such a scenario where your water as a product, combustion product, is in liquid state, the heating value, okay, the energy released will be higher, energy obtained will be higher. So that is the high heating value. And in case where your water is in vapor state, that is your low heating value. Okay. Then also is one more concept, that is the adiabatic flame temperature, which basically is the measure of temperature that is achieved by the combustion products after combustion when your combustion conditions are adiabatic, right? So this is your adiabatic flame temperature. Then one more topic, recuperation is also there, which is basically to increase the combustion efficiency. In which what we do, that the energy that we obtain from the hot combustion products, what we do, we transfer this energy to the air that is being supplied to the combustion process. Okay, the combustion, the air that is being used, to that air the energy from the hot products of combustion is given to increase the efficiency of combustion, right? That is your recuperation. So these are the topics that have been covered in week 8. Then is your week number 9. So week number 9 is on chemical kinetics of combustion, okay, of the combustion reactions. So there is Fick's law, which is for diffusion. To mathematically define the diffusion, Fick's law proves to be very useful. After that, we have topics global reaction and elementary reaction. So what are these? So first of all, first is your chemical kinetics. Sorry, first is your Fick's law. So Fick's law is this. Please remember it is for diffusion, the binary diffusion. Okay, where two species are mixing together. So here this is mass flux per unit area. Okay, this is mass fraction Y, and this is your binary diffusivity. Okay, so this is your Fick's law expression. Then is your global and elementary reaction. So global reaction basically is the whole reaction in a single go. Okay, so if you see some reaction, particular reaction, so in a single step, if we see this reaction, it's a global reaction. But then the elementary reaction is the steps that are there that have been taken to reach to final products. Okay, so elementary reactions are the fundamental reactions that take place behind the scene. Okay, and in front we see the that we have some reactants and then finally we have some products. Okay, so this is your global reaction. But then behind this, there are a lot of elementary reactions that are taking place, basic reactions that are taking place. So these reactions can be unimolecular, they can be bimolecular, and they can be termolecular. Okay, in unimolecular, only one species is involved in the reactant side, and in your bimolecular reactions, two species are involved in the reactant side, and in your third molecular, reactions are three species are involved in the reactant side. So this is your elementary reactions. Okay, so these are your global and elementary reactions. So this is your chemical kinetics. Then is your thermodynamics of reactive systems. Okay. So the thermodynamics of reactive systems. So in this week, we saw four cases, okay, of four types of reactors, right? First one is your constant pressure fixed mass reactor. So in your first two, the mass remains fixed, right? But in the first case, your pressure remains constant, and in the second case, your constant volume remains constant. Okay. So all the discussion on these reactors has been done, right? And then third reactor here is your well-stirred reactor. So well-stirred reactor is your ideal case where your proper mixing of your fuel and oxidizer has takes place. Okay. So here the mixing uh, is apt, but in the plug flow reactors, what happens is that your mixing in axial directions is not possible, right? So this is one difference between your well-stirred reactor and plug flow reactor. Okay. Then one more topic here is conditions for chemical equilibrium. So if we want chemical equilibrium, in that case, there are two things, two properties. One is your Helmholtz function, and another is your Gibbs function. So in the scenario of a chemical equilibrium, what happens to these two properties? So these two properties will be at their minimum value when a particular reaction is in chemical equilibrium, right? So both the Helmholtz function and your Gibbs function, these two will be at their minimum value when the chemical equilibrium is there in the reaction that we are studying. Okay. So your Helmholtz function is defined at constant temperature and volume, and your Gibbs function at constant temperature and pressure. Okay, for chemical equilibrium. Okay. Then is your last 2 weeks, right? So in your week 11, so these 2 weeks are basically on combustion and flames. So here we discuss about flames, basically about flames, and then how the combustion takes place in diffusion type of flames. Okay, what is a laminar flame? What are the properties of laminar flame? So all this has been discussed in this particular topic. Okay, all right. So first topic here is your modes of combustion. So this is your week 11. So first modes of combustion. Topic here is modes of combustion. So first difference is that there can be flame and there can not be a flame. Okay. Then in your flamed combustion, there are two types or two modes. One is premixed and one is non-premixed. Okay. Non-premixed is also known as diffusion. So there can be in combustion there can be a flame and there cannot be a flame, and if there is a flame, so there are two types of combustion. One is your premixed type where your fuel and oxidizer are already mixed before the combustion, and second is your non-premixed or diffusion type of combustion where your fuel and oxidizer they diffuse, they come together, and then combustion takes place. So these are the two modes of combustion. Then is your flame speed correlation. One more topic here is flame arresting methods. So in your flame speed correlations, laminar burning speed can be defined this way. This is the speed of the flame. Okay. So this is the expression for your laminar burning speed SL, where gamma equals to 2.18, this, and your beta equals to, right, and then your SL reference is equals to TPU reference is equals to, and P reference equals to 1 equals. So here TU is the temperature of unburned gases. Okay. Then BM and B2, this, and also phi m. These depend on the fuel type, the type of fuel that we are analyzing. So these constant values depend on that. Okay. Then Y DIL is the mass fraction of the diluent that is present in the air fuel mixture. Okay. So this way we can calculate the laminar burning speed of a flame, of a laminar flame. Then is your flame arresting methods. So different flame arresting methods are as follows, sorry. First is your quenching distance, second is your flammability limit, and third is your minimum ignition energy. So quenching distance basically is that we try actually leads to the arresting of the flame. Okay, and this diameter of the passage for which your flame can be arrested is called the quenching distance. Then second is your flammability limit. Flammability limit basically is the, so this is the range of values. So this is the range of equivalence ratio. So in a particular range, your mixture, air fuel mixture is flammable, and if it is not in that range, in that case, your mixture is not flammable. So this flammability, knowledge of flammability range can be also be used to arrest the flame. Then is your minimum ignition energy that is required. Okay, is required for ignition, and if you don't provide that, your, so in that case you won't be able to arrest your flame, right? So these are the three methods by which we can arrest our flame, right? So these topics have been covered in your week 11, right? After that is your last week, right? That again is on combustion and flames. So here we saw that how the droplet, right? How the droplet burns in case of a diffusion flame, right? So this is a non-premixed type of combustion where first we see the mass transfer. So we have some droplet of fuel, right? And then from its surface, the fuel starts evaporating as it gets energy, right? And this evaporation basically is your mass transfer. Okay, so if we are able to analyze this evaporation in detail, so this is great for the analysis of the whole combustion process, right? So in that context, a discussion has been done on this topic, right? Then the same way, when we get uh, heat, when your droplet receives heat, in that case, what the scenario is, right? So all this has been covered in this topic, right? And one important thing is here is your d square law, which basically is the relation of your diameter of your fuel droplet with respect to time. Okay. Here K is your evaporation constant. This is your d square. Okay. Then next topic here is your droplet burning. So here we saw that we have two regions. One is inner region and one is outer region. So it is this way. Here you have your droplet surface. Let's say this is your droplet surface. This is your flame sheet, and here is your far field. Okay, so this is your outer region. This is your inner region. So while combustion, what happens is that your fuel comes from your this droplet by means of evaporation towards the flame, and your oxidizer comes from your outer region, right? And this way your combustion takes place when these two reactants, that is fuel and oxidizer, react at your flame sheet. Okay, so this is your droplet burning. Then same way, these rocket engines have been discussed where combustion is taking place by means of diffusion, right? So these are all the topics that have been covered in this course, right? So it was a 12-week course. I'll just conclude this session, right? So there were 12 weeks in this course. So in first 5 weeks, we basically did some concepts of thermodynamics. Some were basic concepts and some were advanced concepts, right? Where we saw discussion on entropy, exergy, and then we also derived the thermodynamic property relations, right? After that, your next section was from week 6 to week 7, right? So it was week 6 and week 7, where we did discussion on our gas mixtures. So this is from the perspective of fuel and oxidizers, right? So when they mix during combustion. So in that case, to put things in perspective, discussion has been done, right? So this was your second section. After that, your last section is on combustion, right? Where we initially started with the basics of combustion, stoichiometry. Then we saw the rate of these chemical reactions that take place during combustion reaction, right? After that, we did thermodynamics of reactive systems. So the thermodynamics that revolve around these reactive systems, that has been discussed. And at last, the discussion revolves around the flames, right? The flames One is your laminar type of flame, right? Then is basically there are two types of flame. One is your premixed flame, and then is your non-premixed flame, that is diffusion flame, right? And the last this week discussion is mainly on diffusion flames, though turbulent flame has been touched upon, but main discussion is on diffusion flames because we have done topics like diesel engines, gas turbine engines, and rocket engines. All these have been covered. All right. So this was your course, Advanced Thermodynamics and Combustion, and I hope that this course was a learning experience for you all, right? And for this session, I'll then sign off here only. Okay. Thank you for attending this course, and best of luck for your exams. Okay. Thank you. Bye.